The blue whale weighs up to 200 tons. For decades, this wasn't just considered the largest animal alive, it was considered the largest animal that could ever physically exist. Not because evolution lacked the time or opportunity to build something bigger, because the laws of physics themselves were assumed to draw a hard ceiling right around this exact size. Go any larger, and a body should collapse under its own weight. Then a jawbone was found that broke that assumption completely. This is ichthyodotin, and it represents the only confirmed time in Earth's history that something came close enough to challenge the blue whale's claim to being the largest animal that has ever lived. It wasn't a whale, it wasn't even a mammal, it was a reptile. Before comparing sizes, we need to agree on what large actually means, because length alone is a misleading metric. Argentinosaurus, a dinosaur, measured around 115 feet, comfortably longer than any blue whale. But most of that length was a thin neck and an even thinner tail. Structurally, it was closer to a suspension bridge than a tank, topping out around 80 to 90 tons despite the impressive length. The bootlace worm can reach 180 feet long and weighs roughly as much as a wet sock. That's not size, that's just a very long piece of string. A blue whale earns the title through raw mass, a dense, solid 200-ton block of muscle and blubber. So the real question becomes whether ichthyodotin could match that mass, not just its length. Estimates put ichthyodotin at roughly 85 feet long. Not a skinny technicality either, this thing was thick, genuinely massive. The largest known specimen, found in the UK, is estimated at around 120 tons. That's the equivalent mass of 13 Tyrannosaurus rexes combined. But the average ichthyodotin estimate runs closer to 80 tons. Compare that to the blue whale's upper limit of 209 tons, and the whale appears to win easily. Except that 200-ton figure represents the blue whale's absolute maximum, not its typical size. The average blue whale actually weighs somewhere between 100 and 150 tons, landing in almost exactly the same range as ichthyodotin's 80 to 120 ton estimate. This isn't being engineered into a close match for dramatic effect. We genuinely don't have enough data to give a definitive answer, and that uncertainty itself is the most important part of this story. We have measured thousands of blue whales directly, because they're alive and not particularly good at hiding from researchers. For ichthyodotin, we have found exactly 2 jawbones, total. Think about the statistical implications of that for a second. Out of potentially millions of individuals existing across millions of years, what are the actual odds that the 2 specimens we happen to recover represent the single largest individuals the species ever produced? Functionally 0. This is where a second, earlier discovery becomes critical. Years before ichthyodotin was formally named, scientists recovered a different, much older jawbone at a site called Ost. It clearly belonged to an ichthyosaur, but it was so comically oversized that researchers hesitated to even classify it properly. Nobody wanted to be the paleontologist who claimed to discover a genuine sea monster and turned out to be wrong, so the bone sat in scientific limbo for years. Once ichthyodotin was officially described, researchers looked back at the Ost specimen and reached an unavoidable conclusion: this was likely the same species, or at minimum the same general type of giant. And the Ost bone is larger than either confirmed ichthyodotin jawbone. Running the math on standard ichthyodotin remains produces that 80-ton estimate. Plugging in the Ost specimen instead pushes the length to nearly 95 feet and the weight to roughly 175 tons. Still technically under the blue whale's recorded maximum of 209 tons. But the Ost specimen almost certainly wasn't the largest individual of its species either. If we treat that 175-ton estimate as representing an average large adult, the same way 120 tons represents an average large adult blue whale, and then scale upward using the same growth pattern observed in modern whales, the math gets genuinely extreme. In blue whales, the absolute largest recorded individuals run roughly 60% heavier than a typical large adult. Apply that exact same growth curve to ichthyodotin, and the theoretical maximum size for the species isn't 175 tons, it's closer to 280 tons. That number would completely surpass the blue whale's confirmed 209-ton maximum. This remains speculation, not established fact. We don't know with certainty that Os colossus represents the same species. We don't know if it was anywhere near the largest member of that species, and we don't know with full confidence how its body mass was actually distributed. But here's the honest bottom line that survives all that uncertainty. This animal was very likely larger than the published average estimates suggest. And the most probable scenario is that the largest individuals of this species genuinely exceeded the largest blue whales ever recorded. That makes this an unusually strange case in evolutionary history, because typically mammals are the ones that get massive, not reptiles. Being a whale is mechanically difficult. As a mammal, you're carrying lungs full of air and a thick insulating layer of blubber, essentially a giant buoyant balloon. Without extremely dense, heavy skeletal bones acting as ballast, a whale would simply float uselessly at the surface, unable to dive. Reptiles are typically built for a completely different purpose: speed, agility, the ability to snap something in half quickly. A mosasaur looks genuinely terrifying, but compared to a whale, it's almost athletic, long, lean, carrying none of that extra insulating mass. Ichthyodonton was an ichthyosaur, just a colossal one, and despite looking remarkably like a dolphin, it remained fully reptilian. This resemblance isn't coincidental. Its convergent evolution, dolphins, sharks, and ichthyosaurs all independently arrived at the same torpedo-shaped body plan because basic physics demands it for efficient, fast swimming. So why would a reptile built for speed carry this much mass? Because Ichthyodonton lived fully pelagic, far from any coastline, in open, deep ocean. Swimming thousands of miles across open water makes being small a genuine energy liability. Physics dictates that larger bodies experience proportionally less drag relative to their mass. Precisely why a massive cargo ship moves more efficiently across open ocean than a small speedboat. By becoming an 85-foot living torpedo, Ichthyodonton could cover enormous distances without burning through its energy reserves. The exact same fundamental strategy blue whales use today. Mass also solved a second major problem: cold. Even during the Triassic, deep ocean water runs near freezing, and reptiles generally struggle badly in cold environments. But once an animal crosses a certain size threshold, it unlocks something called gigantothermy, becoming so physically large that body heat simply cannot escape fast enough to cool the core. The animal functions as its own living thermal battery, allowing it to hunt comfortably in cold water that would otherwise be lethal. None of this size works if gravity crushes the structure outright. Fortunately, gravity doesn't function identically underwater. On land, the structural limit for an animal sits around 100 tons, anything heavier, and the legs simply snap under the load. In water, buoyancy carries the weight instead. No legs required, just float. This is precisely why the largest land animals capped out around the Argentinosaurus range, while marine animals like the blue whale and Ichthyodonton could push straight past 200 tons. There's one final requirement though, arguably the most important: food. You could possess the perfect body for reaching enormous size, but with nothing available to eat, you simply starve regardless. Fortunately, the late Triassic Ocean was an absolute buffet packed with massive cephalopods, oversized fish, and other large marine reptiles. The available biomass was more than sufficient to support a predator at this scale, and the penthouse was completely empty. No whales existed yet. No megalodons, no mosasaurs. Once Ichthyotitan crossed a certain size threshold, it had zero genuine rivals. Natural selection had only one direction left to push bigger, so it did. It became the uncontested king of the ocean. And then it vanished completely. Around 201 million years ago, the Triassic period ended, and not peacefully. The end came via the Central Atlantic Magmatic Province, essentially the Earth's crust cracking open and releasing lava continuously for thousands of years. This triggered massive carbon dioxide release, accelerating global warming and acidifying the oceans worldwide. This didn't kill Ichthyodonton instantly. what it killed first was its food supply. And this is exactly where the strategy of being an 85-foot biological submarine turns into a fatal liability. Massive body size is a genuine advantage when the food supply is unlimited. The moment that supply collapses, massive body size becomes a death sentence instead. Ichthyodonton needed enormous daily caloric intake just to function. When the surrounding ecosystem crashed, the largest animal in the ocean starved first. Ichthyosaurs as a broader group didn't disappear entirely. They survived into the Jurassic period, but they changed dramatically. They got smaller, they got faster, they stopped trying to be cargo ships and started evolving into something closer to fighter jets. And strangely, the ocean never produced another animal at this scale again for an extraordinarily long time. For the next 200 million years, marine reptiles like Mosasaurus and Pliosaurus dominated the oceans. Genuinely large and dangerous, but nowhere close to Titan scale. A large mosasaur tops out around 10 to 20 tons, essentially a rounding error compared to Ichthyodonton's mass. That ecological niche of true ocean giant sat completely vacant for 200 million years, until mammals eventually returned to the water roughly 50 million years ago, evolved into whales, and learned to filter feed on krill at scale. Ichthyodonton was a one-time experiment, a brief evolutionary window where a reptile reached the absolute physical limits of biology, and proved decisively that the blue whale wasn't the only animal capable of reaching 200 tons. It was simply the second. We have recovered exactly 3 relevant bones total across this entire story, 2 confirmed Ichthyodonton jaw bones, and the single Ost colossus specimen. In the broader context of paleontology, that sample size is a statistical rounding error, less than 0.01% of all animal life that has ever existed became a fossil at all, and we have only recovered a small fraction of that already tiny fraction. We are effectively reconstructing an entire library's history from 3 torn pages found in the trash. And the fact that we found these specific bones at all is genuinely suspicious in a useful way. If 200-ton animals were truly 1 in a billion evolutionary freaks, the odds of randomly discovering their fossils on an ordinary beach in England should be close to 0. The fact that we did find them implies they may not have been nearly as rare as we assume, which raises the real question this story leaves open. Is 200 tons genuinely the biological ceiling, or is it simply the ceiling of what we've managed to dig up so far? It's entirely possible that buried under a mile of rock somewhere, during a peak window of oxygen and food abundance, something existed that dwarfed even these giants and then vanished completely without leaving behind a single trace we've ever recovered. Whatever Ichthyodonton actually represents in the full picture, it wasn't simply a big animal. It was a lost experiment, the only confirmed instance in this planet's history where evolution pushed a reptile to true giant scale, rivaling anything a whale has ever produced. The blue whale now rules over an ocean that a reptile had already conquered, at this exact scale, over 200 million years before the first whale ever existed.